In the warm work region here, which is hard to say, you have a small decrease in strength and you have a larger increase in ductility. So that allows you to do further work on the part. So if you got most of the way through working on the part and you needed to do a little bit more, you could do this, especially if you're trying to retain the strength hardening or the strain hardening that you had already achieved. So lots of grain growth in hot work, lots of the recrystallization. It's forming a completely new crystal structure. It will react with the environment a lot, and so we often don't want to keep it there for a long time if we can help it. Doing things here in the recovery region, we don't actually do much work there, but we will heat it up, try to anneal it, try to get a little bit of the ductility back, and then cool it back down, and then we do the work as cold work generally. One of these is going to make me go forward. That is the one. Those. Okay. One of the concepts that I talked about just a little bit was whether the flow stress is dominated by the strain or by the strain rate. So in cold work, we are working the material, the dislocations are moving, slip planes are slip is happening until the dislocations lock together or they lock into impurities, and then that causes you to have to apply a greater stress to be able to continue to deform the part. And so in cold work, the flow stress is dependent on the strain. But in hot work, it is not dependent on the strain, or it can be, but is more dependent on the strain rate. And that's because it is constantly reforming the crystalline structure. So if I strain it and I lock the dislocations together, it will very rapidly start to reform the crystalline structure. Diffusion is happening really quickly if the dislocations had gotten locked against impurities. And so it only increases the flow stress if I am straining it faster than it's recrystallizing. So if I work really, really fast, then I will see an increase in flow stress and I will have to put more into it. If I want to retain any of that increase, any of that hardening that I'm getting or that strengthening that I'm getting, I have to quench it very quickly before the grains can recrystallize and grow. And so in hot work, it is more dependent on the strain rate than the amount of strain. So we, on Thursday, are going to look at some processes, and we're going to try to we're going to watch them, and we're going to try to understand why do they work in one area and then go off and work in another area. And it's all going to be, a lot of it's going to be based on this. All right. That says the same thing. We'll skip that. And that. What we need to get to is metal forming. So we get these big pieces of metal, we need to form it into a different shape. We can cast it into a different shape, but sometimes casting leaves us with a material that we don't know the properties of very well. It may not have the grain structure that we want. There are all kinds of things that may not be good about it. And so we may want to get to the material by another method. And so we're going to talk about the bulk forming method. So this is essentially taking the metal and squishing it to be the right shape. You don't need to copy all these down. Next class we're going to talk about rolling and forging. Class after that we'll talk about extrusion and drawing. And then after that we'll get to sheet metal, which is shear spinning and stretching, bending, and contour bending over there on the right side. So these are all the ways that we can just take the metal and depend on the fact that it has these free electrons, so we're able to deform it more than we can deform most materials and have it retain a lot of good properties. So the first thing that we need to do with this is we need to talk about the stress kite. So here we go with the stress kite. If I have a material and I start to deform the material. So maybe I'm pulling on it, maybe I'm squashing it. What we need to understand is how much force or how much stress do I have to put in it before it starts to deform. And so there are two famous people who worked on this, and a whole lot of other people have worked on this. But when you have a stress state like that, you will find that there are two axes that dominate the motion and the stress in the material, and you can sort of devolve whatever forces and whatever stresses you're putting into it, and you can find two orthogonal axes that will have the greatest amounts of stress. So we're going to call those the principal axes, and we're not going to worry about how we got the principal stresses in the principal axes. We're just going to assume that they occur. Okay? Now, that all seems good. If we were on this graph, this side is tension and this side is tension. And this side down here is negative, so it is compression. It is minus sigma 2, and this side over here is minus sigma 1, so this is also compression. All right. So if I have a material and I uniaxially pull on that material, what is the flow stress that is required to begin deformation in the material? It is a sort of trick question. It is the flow stress. It just takes the flow stress. So out here somewhere, I'm going to put the flow stress. Okay. Now, if I didn't load it in the sigma 1 direction, but I loaded it in the sigma 2 direction and I pulled on it, similarly, it would take the flow stress to move it there as well. And we're going to make a wrong assumption right now, but it's close enough for us to feel good about ourselves. I mean, mostly good about ourselves. That if we were to compress it, we would just have to achieve the flow stress in those directions. This is not actually true because in compression, the material fails a little bit differently, but for simplicity's sake, we're going to assume that it's true for right now, because it's not far off. So the question is this. If I take a material and I start to stretch the material in this direction, and at the same time you're grabbing it in the other way and you're trying to stretch it in the other direction, is it going to be harder or easier for me to deform the material in the direction that I want to? Do you think? It seems like it could be easier. I mean, it's kind of a little bit mind-bending. It seems like, wow, I'm putting a lot of energy into that. But it turns out that you're actually fighting each other. And so while I'm pulling this way and you're pulling this way, I have to work a lot harder to get the material to deform. And if I were to pull in this direction and you pushed in this direction, you would actually help me and we would deform the material much more quickly. So when we look at this, if you pull in tension in this direction and I pull in tension in this direction, and we plot that out, we actually get a flow stress up here, which is the combined flow stress. And if you were to trig this out, the distance from here to the center. So what we're concerned about all the time is the distance from our current location to the center, because that's the amount of stress that we're having to put in the part. And so this is 1.414 times the flow stress. So because you're pulling in the opposite direction that I am, we're working against each other, so I have to pull 1.414 times as hard to get this material to deform. And we're going to make the wrong assumption, but it's not a bad assumption, that also happens in the compressive direction. So it would be minus 1.414 times the flow stress to deform the part if we were down here. So that's the distance to the center. Now, yes?
Are you saying you have to pull 1.414 times harder than the person pulling?
No, I just have to pull 1.414 times harder than I would have had to pull if that person was not pulling.
Oh, okay.
Yeah, so just 1.414 times what I would have if it were just the material. Yes?
Is that for the same deformation or for what?
That's to start deformation.
Oh.
That's to get into the realm of deformation. Okay, now if I'm pulling on it really hard and you start pushing on the sides, you're helping me out. You're helping to make it longer. As I pull on it, you squash it on the sides, it gets longer, life is good, we're working together, and things are easier. And so if I were to draw a line across here, and in that case, I am pulling on it and you are pushing on it, it turns out that that point maps out to right there. And it is, depends on where you go here, but it's sort of sigma f over root 2. Okay, so it's less. It's 0.707 times sigma f. Okay, that's pretty cool. 4.707 sigma f. Okay. So if the same thing happens over here, if you start pulling and I start pushing, we get to the same point over here. So this is called the Tresca failure criterion. And so when, and I call it the stress kite. So when Tresca developed this, what his goal was to understand if I have something, it is under combined loading. So I'm not just loading it in one direction, it's being loaded in multiple directions. How do I know if it's going to fail or not? And so Tresca created this stress kite, and anything inside the kite will not start to plastically deform, and anything outside the kite will start to plastically deform. And then shortly after this, a person named von Mises came along and said, well, yeah, this is all simple and stuff, but really I reject your kite and I substitute an egg. And it is a more elegant solution that gets to this, but it's also less conservative. One problem with Tresca is that here, you know, people were designing for this point to keep the part from deforming, but really they were leaving some design on the table. They could go further and still have the part not deform. Now, of course, we're in manufacturing land, so while everybody else in the world wants to live inside the egg, we want out of the egg. We want to live on the outside because we're trying to deform the material to make something. So we're going to analyze things and try to find a way outside the egg. So we want to be putting in enough of a combined stress loading that we end up outside the egg. There is one other point that is worth noting here, and it is kind of an odd point. There is a minimum on this curve. That minimum happens right here, and this is square root of 3 over 2, or approximately 1.15 times the flow stress. There's one of those on each corner. There's one there, there's one right here. There's also one up here and one up here. So this is sort of a weird region. This is called plane stress. And we'll talk about what this means. What it comes down to is, remember this minus 1.414 sigma f was if I was pulling on the part really hard and you were pulling it in the opposite direction. But this 1.15 sigma f is where I'm pulling on the part really hard and you're not pulling on it, you're just holding it. You're not actively pulling, you're not actively pushing, you're just keeping it where it is. And so that's what we will assume. Yeah?
Do you see examples of this being used in manufacturing for designing a product, or do you see this in designing a way to alter the product and actually like whether it's in forming or something like that.
Yeah, so
Are you-
where do we use this? Or,
Are people on the inside or the outside of the kite?
well, both. So the person designing the part is designing the part to be inside the kite.
Yeah.
And for manufacturing, we're figuring out how to be outside the kite to deform the material into both the shape and the material properties that the user needed or the designer needed so that the part would stay inside the kite.
And then your comment with the part, not the extremes 1.44, but the,
The 1.15?
no, it's the over root 2. Where there was.
This one?
Yeah, you said there was material left behind, as if they were.
Well, it's just if you use the kite, it's
Yeah.
overly conservative.
Exactly.
So if you go with the von Mises, there's a little bit more, so there's more margin here. You could put more stress into it and not actually get it to deform until you get out here.
I see.
Yeah. Okay, yes?
Is the 0.707 down there, is that represented as negative or not? Just cause I noticed that you put negative in front of the.
Yeah. No. Well, yeah, it only matters, so negative here means we're doing compression, and positive means we're doing tension. So if we have more tension than compression, then the tension would win. So then it would be 0.707. The sign here is a little squishy. Here's what we need to get to with this. So when you are doing finite element analysis, you will often plot the von Mises stress. And that will show you in colors, it will say, oh, it's red, it's going to fail. It's green, it's not going to fail. Well, what is it comparing it against? It is comparing it against the stress egg. So it has the way that it calculates the stress egg, and it's comparing it and finding out, am I in the egg or out of the egg? What we're going to use it for in this class, we're not going to calculate these, but what we're going to use it for is we're going to evaluate processes as they are happening, and we're going to try to understand where are we on this graph. Like, is it a process where we are both pulling on it in one direction and pulling it on the other direction? If it is, then we know that we have to get to a higher stress to be able to start to deform the material. Or is it a process where I'm squashing it in one direction and stretching it in the other? Or the other way that this happens is shear. If I'm taking the part and I'm just pushing it over to the side, then it actually takes less stress to deform the part. And so we're going to use this to analyze processes to try to understand how the process is either using this to help it, or whether it is being impeded somewhat in the process by the stress state that we're in. For instance, let's see. There is the official version of it. If you would like the official version of it so that it has more. But this has several things that show you places that this is relevant. So if I am stretch forming something, so if I have a piece of sheet metal, one way that I can make it into a shape is I can hold it on the edges and I can just push really hard onto something that is the right shape. And if I push hard enough, I will end up with the metal deforming to that shape. And so, yeah, there are lots of sort of things that are curved in two axes are often made in this way. And we'll see another one where we do that explosively, and it's just awesome. Yes?
When we're talking about the full compression from both directions.
Yes.
Is that something we use often in manufacturing? Like, is that a real situation, or is that sort of a hypothetical corner?
It is a real situation. So if you're going to see, probably for next class, impression dies, so closed impression dies. So you have something that I want to make a complex shape. And so what I do is I machine the inverse of that shape in two pieces of metal. I go whack, 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 over and over and over until I just beat it into that shape. Well, what I'm doing is I am putting pressure in this way, and it's trying to squish outwards, but also the shape is curved in there, and so it's also applying pressure in both directions. And so when in that case, I have to achieve a much higher force to actually get there. Yeah.
I noticed that you had like your little shear diagram for your chip there.
Yes.
Is a concept of like chip load, does it derive from something like this with the von Mises?
It is. Yeah, some of the chip load understanding is derived from this. And so when you are forming a chip, it is a shearing action. At the same time I am pushing to the side, I am also forcing the chip up the face of the tool. And that shearing action makes it actually easier for me to go in and remove that material.
What do you mean by chip?
Chip, the chip is when I am cutting, so this is a picture of a cutting tool.
Oh, I
You
see.
can clearly see it, no. So this is a cutting tool, and this is the material, and as the cutting tool is moving forward, this little thing that comes off it is called a chip.
Okay, I thought you
So-
were making like an actual chip.
No, it would be good. That is on one of my slides, we'll find that, there are tortilla chips on the slide.
Sorry, I didn't know it was you.
Never pass up a dad joke. Okay. Never skip a dad joke.
Metal chips are strong.
All right, so a place that 1.15 weirdness happens, this little weird place down here, actually turns out to happen a lot. So if I were to take something and constrain it on the sides and mash it in the middle, that would be in the 1.15. Because I'm not actively crushing it on the sides, but I'm also not letting it move. Well, you look at that and you say, that's dumb, don't do that, it makes it harder. But when I actually take a part and I squash it between two dies, so here's just a part, I'm squashing it between these two dies, it turns out that the friction on this face will not let the part get wider. And if the part is pretty thin, so it can't bulge out the sides very well, then I end up with this case also, and it's like I put these rails on the side to prevent it from expanding. But it's really just the friction on the die won't let it expand. And so we do a lot of things to try to get around that. We try to reduce the friction on the die, and then we live with it. Okay. So, yes? Do you have a
That's where you
question?
get, I actually wasn't question, but that's where you get the bulge from then.
The bulge on the side, yeah. So you would get a bulge on the side from this, but even with the bulge, it's still restricting it because the material that's here in the middle being squished, you know, it looks at its neighbor and says, hey, I'm getting squished, I want to move over to the side, and its neighbor says, I don't have anywhere to go. And you know, all of these little bits all along here don't have a place to go. It's only right at the edge that someone says, hey, I want to move over, and the other one says, okay, it squishes out to the side. So in the middle, for most of the part, it is experiencing this where it can't get wider, and it's only the edges that are able to barrel or, yeah, move over the sides. Okay, so just to remind you, this is combined stresses. What we're dealing with here is combined stresses. How do I determine what happens when I have stress in more than one direction at a time? So combined stresses, von Mises stress egg, or Tresca stress kite. All right, friction. Remember in physics when they talked about friction and they said, you know, static friction is mu s times the normal force, or they said kinetic friction is mu k times the normal, they lied. I mean, they didn't lie, they just kind of stopped early. They were like, well, and then stuff breaks down. So if you actually plot stress, I mean, the people in the physics department, they do this all the time. They tell you, well, if you're an engineer, I'm going to tell you the simple version, then go away, we'll discuss the hard one. Anyway, so It does actually look like that for a while. You load something up, so we just have something and we're loading it. And for a while, it is true that it's a linear relationship and it depends on what the coefficient of friction is. But there is a point where all of these curves will go off to the side. Like, what? What do you mean? If I press really hard right here, it's no longer gonna hold it? What's going on? Well, the material fails. When you get to this point right up here, I am pressing on it so hard that the material's just gonna squish out to the sides. It's gonna shear rather than hold. And so one thing that we find in manufacturing is we get to loads where the friction quits. And well, the friction doesn't quit. The friction is still there, but the material gives up. And instead of being stuck by the friction, the material just shears off to the side. And that's actually good for us because we need to reform the material. So we wouldn't want friction to just completely limit what we can do. Look at that, it says end of slides. I guess that's the end of the slides. So what we're gonna be doing in the next couple of weeks is we're gonna start talking, we're done with material science from a material science sort of way. So from now on out, it's all about processes. We're gonna learn about manufacturing processes, but we're gonna analyze them with these things. So we're gonna take these concepts we've learned. We're gonna look at them and we're gonna analyze, is there combined stress in this? We're gonna look at them and we're gonna say, what does constancy of volume do to me in this case? We're gonna look at it and we're gonna try to understand what flow stress we have to achieve, and we're gonna look at it and we're gonna figure out, are we cold working, are we hot working, and what is that doing to our process? Is it making our process more, our material more ductile or more brittle, and do we have to do something about it? So that's where we're headed. Last thing, for lab today and on Thursday, you should consider bringing a jacket. We will be outside, so we'll meet in the hallway, be on time. We'll go out in the backyard under the canopy. So if you are late, go down the hallway that's next to the manufacturing lab, out into the back parking lot, and we'll be out under the canopy. We will be pressing sand molds. We don't have the cool concrete thing, so it's gonna be you and, I don't know, just something to pound with. And then we will also be playing in plaster of Paris and making an incredible mess and trying to create investment castings as well. And each year, we only get to do this twice a year because we have to use the art building facilities. And each year we try to make it a little better, and it's totally an experiment every year about whether it's gonna work or not. So some years we're somewhat successful, and other years we just create a lot of smoke in the art building, and that's not all bad either. So anyway, that's where we're headed this afternoon. Meet in the hallway in Thursday. All right, have a good day.
You want these?
No.